method of initial rates problem. This is the practice problem I had asked you guys to complete on your own. So if you've not already completed this one, please go back and attempt it before watching the rest of this video. So if you're continuing watching the video, I'm going to assume that you've given this a try. The method of initial rates allows us to establish the differential rate law. In general, it's going to look like this. You're going to have some type of rate constant, which we're going to have to figure out. It's the last thing that we can figure out. The rate is a function of the concentrations of the reactants here. Okay, so this bromate ion is going to play a role, but we don't know its role yet. The power or the order of bromate is unknown for the time being, so we'll just give it an exponent of n. And we're going to see throughout the course of this unit, it's very common for n to be one of three values. N is often 1, 2, or sometimes 0. Okay, it's very rare for n to be something other than one of these values. And let me talk about what it would mean if bromate was if that ion was 0 order, or if it was first order or second order. Let me just discuss what that would mean. Okay, so if bromate was one of these, what would that mean? It's probably one of these. If it's 0 order, if you think about concentration, some number in molarity raised to the 0 power, whatever that number happens to be, when you raise it to the 0 power, that quantity equals 1. And so what that means is if you have a 0 order reactant, or zeroth order, what it means is the concentration of that substance or that species plays no role on the rate of reaction. Okay? So even if that number changes, say it's dropping or increasing or whatever, it wouldn't matter. And so in the rate law, if this expression contains a 1 in it, and we're doing a bunch of multiplication in here, even if that concentration is actually changing, its concentration plays no role on the rate. If bromate concentration is raised to the first power, well, then it would be important. And one way to think about that would be if this is first order. If it's first order, then if you double the concentration, say if you used double the initial concentration for that ion, double the concentration would generate double the rate. Okay, so call that directly proportional. That's the better way to state that relationship, right? If you triple the concentration, you would triple the rate. If you cut the rate in half, if you cut the concentration in half, it would cut the rate in half. Directly proportional. So whatever happens to this concentration, in terms of multiplication or division, the exact same thing would happen to the rate. Okay, and it's not really possible to say like what that would equal. All right, it would be changing. It's kind of like an x, so it'd be changing, and so the rate would also be changing proportionally. If it's second order, okay, this is sort of like x squared, and so there is a connection here. There's a direct connection, but it's a quadratic connection. So if you have a second order reactant, if you double the concentration, it's going to generate 4 times the rate. And the reason for that is that squared term right there, right? 2 squared, if you had whatever this value is, if it was, say, 1, well, 1 squared is just 1. If you double the concentration, you're going to get 4 times the rate. And if you, say if you triple the concentration here, right? So if I triple 2, for instance, that would be 6. Okay, 6 squared. Well, what's happened to the rate? If I tripled the concentration, I've actually increased the rate by a factor of 9. 9 times the rate from tripling the concentration. And that's because 3 squared is 9, okay? So you have to look for connections like that. If there's a directly proportional relationship, your order of reactant is first order. If there's sort of a squared connection, then your reactant is second order. So that's what the significance of these orders of reactant are. So let's go ahead and finish up writing this rate law. We've got other reactants in this one as well. Bromide ion, and it's not necessarily the same order, so we give it a different letter. Normally M, it doesn't really matter what you call it. And then H+, hydrogen ion, and we'll just call that L. Okay, doesn't really matter what you call those though, but you should label them with different letters, normally N, M, and L. It's kind of like alphabetically backwards. Anyway, so let's have a look and see what's going on here. In the first experiment, we've got 0.1 molar everything and the initial rate, okay? In the second experiment, you can see that we've held these guys constant, but we've doubled that concentration, okay? That's the only change that we made, and sort of the output on the rate is twice the rate. That tells us that this ion, bromate ion, is first order. And so there's 2 ways you could justify this in a free response problem on the AP exam. You could state it in words, or you could show the ratio of those 2 experiments like we did yesterday. So let me do it mathematically, and then I can state it in words clearly. We're trying to establish that bromate is first order. So mathematically, we would say rate from experiment number 2 divided by the rate of experiment number 1. And you write out the rate law, the general rate law, and you plug in the concentrations raised to their powers and set it equal to the actual rate. And so the rate in number 2 was 1.6 times 10 to the negative 3 molarity per second. And the rate in reaction 1 is 8.0 times 10 to the negative 4 molarity per second. Those are their rates. We set that equal to the rate law with the values plugged in. We don't know what K is yet, so we just leave it there. Plug in your values, 0.10 molar raised to the n power times, let me zoom in a little bit so I can maybe hopefully write a little smaller here. All right, everything's 0.1, and oh goodness, that's supposed to be experiment 2 up top. Please forgive me. Experiment 2 goes up top, and in experiment 2, it's 0.2 molar bromate. Okay, raised to the n. Everything else is 0.1 molar raised to the m, and 0.1 molar, this one here, hydrogen ion concentration, raised to the L. The first experiment everything was 0.1 molar. N, 0.1 molar. Bromide ion, raised to the M, 0.1 molar. Hydrogen ion, raised to the L. Okay, now, this ratio right here, we're just dividing the rates, and we can see that the second rate is 2 times the first rate. Units divide out. 2 times the first rate. That's what that equals. And here we can divide some things out. The K's divide out. The bromide raised to its power divides out, and the hydrogen ion raised to its power divide out. And all that we have left here is this little bit. And up top it's 0.2. On the bottom, 0.1. The numerator and the denominator are being raised to the n power, so it's just like we took the whole fraction and raised it to the n power. And of course, that simplifies down to 2 raised to the n power. So n must equal 1. 2 raised to the n power equals 2. N has to be 1. Okay, so we've just proved that bromate is first order. And this one right here is first order. Okay, now the way that you could state it in words if you wanted to go that route, you could say simply, when holding all other concentrations constant, doubling the concentration of bromate ion doubles the rate of reaction. Therefore, that's the symbol for therefore, bromate is a first order reactant. Okay? And that's sufficient justification. Okay, but you do have to state very clearly, you know, everything that you mean. Okay. It might be even important to mention like comparing reactions 1 and 2. So, but when holding all other concentrations constant, that's important. That tells us that the effect, the reason we have a different rate here, cannot be anything to do with the hydrogen ion or the bromide. We didn't change them. We've controlled for that, and this is the only thing that we've changed. That's our manipulative or manipulated variable, and that's our response variable. Okay? And so that's how we can justify it. And so now I'm going to justify it in words for the other ones. Okay? So let's clean this up. All right, and let's have a look at some of these other ones. When we compare, let's see, between reaction 2 and reaction 3, experiment 2 and 3, we've held that constant, we've held that one constant, and we've doubled that one. Okay, so we've doubled here, and here we can see the rate also doubles. 16 goes up to 32. The power of 10 is the same, so we can kind of compare 16 to 32. That's twice the rate. 2 times that, 2 times that. Okay, these little notes I'm writing is not a clear enough justification. Go ahead and state it in words. This is directly proportional. Bromide is also a first order reactant. Okay. Bromide is first order. Because when its concentration is doubled while the others are held constant, the rate doubles too. Okay? So that tells us that m is also equal to 1. M equals 1. And then finally, let's see the effect of hydrogen ion. Now you got to be careful if you're changing multiple things from one experiment to the next. You can't really think through why you're getting the effect that you're getting. So you need to find two experiments of the same reaction where you're only changing one thing. So if we compare experiment 1 and 4, there we can see we held bromate constant, we held bromide constant, and we've doubled hydrogen ion concentration. Okay, so let's compare these rates here. Okay, so you got to be careful if you have different powers of 10. But 8 to the negative fourth, 8 times 10 to the negative fourth is 1/4 3.2 times 10 to the negative 3. This is 4 times the rate in this experiment here. If you can't see that, there's no shame in using a calculator to compare those. And I always take the larger one and divide it by the smaller. Okay, so here on my calculator, if you do 3.2 times 10 to the negative 3 divided by 8 times 10 to the negative 4, or there you can see it's 4 times the rate. Okay, so that is not a first order reactant. H plus concentration really affects the rate. Okay, so when we double its concentration, we've quadrupled the rate. Okay, and if we had, for instance, done a reaction with 3 times, you know, like if we had used 0.3 molar of that stuff instead of 0.1, we would have seen this increase by a factor of 9, because 9 is 3 squared. So it's not just double or something, it's the square of how we've changed the concentration. Okay, so that tells us that H plus, L, the order of H plus, is second order. Okay, so when H plus, and that's probably faster to write than talking about concentration, when the concentration of H plus is doubled, while other concentrations are held constant, rate of reaction quadruples. Okay, so therefore H plus is a second order reactant. Okay, and that means L is 2. So that's enough information to write out the rate law. A lot of this video was explaining how to justify our responses here. We've justified each one. You can always justify it mathematically if you prefer writing it out like that. That's always enough to justify it mathematically that way. But the rate law then, if that's what we're trying to figure out, we would just simply say, and I've run out of space, but we could say here, and I'll put it in a different color so it stands out. The rate of that particular reaction is proportional to bromate concentration raised to the first power, bromide ion concentration raised to the first power, and hydrogen ion concentration squared. That would be the rate law. That's called the differential rate law. Now, if needed, we can solve for the value of K, the rate constant. Okay, and I showed you how to do that yesterday, but you could literally pick any of those trials up here, any of these ones up here. Experiment 1, 2, 3, or 4 would all work. Plug in your values, these actual numbers, into the rate law, set it equal to the rate, and then divide through, and you can find K. So if you haven't done that already, pause the video now, try to solve for K, and then check in just a moment. Okay, so I'm going to plug into the first value. So the rate in that first one was 8.0 times 10 to the negative 4 molarity per second. And just make sure I'm not doing anything silly. There it is, okay. And everything was 0.1 molar. Okay, everything was 0.1 molar. So bromate ion concentration was 0.1 molar. We raised that to the first power since N is 1. Bromide ion concentration was 1 molar in experiment 1. And hydrogen ion concentration was 0.1 molar. That's raised to the second power. Okay, so how can we solve for K? Divide everything, divide both sides by all these values over here. Okay, and so also take units into account. That's probably important, but it's definitely important, I would say. Okay, so K, we're going to divide through and basically move all of this stuff into the denominator. All right, so K equals 8.0 times 10 to the negative 4th molarity per second, and we're going to divide by, well, 0.1 times 0.1 times 0.1 times 0.1 again. Okay, so that's 0.1 to the 4th power, but I'll just write that out here. 0.1 times 0.1 times 0.1 squared, right? And the units is molarity to the 4th, molarity times molarity squared. So this is all molarity to the 4th power. And so we can deal with the units right now. One of these molarities divides out. So that's molarity to the 3rd power. And that's it. That's what happens to the units. So now let's type in the actual numbers into the calculator here. So I'm going to type that into the calculator. Here we go. So I've got 8 times 10 to the negative 4 divided by, and put it all in parentheses, 0.1 times 0.1 times 0.1 squared, which is just times another 0.1. Boom. And our answer is 8. Okay, and so 8 with two significant figures, 8.0. The units are per second and molarity to the 3rd also in the denominator. So you could say molarity to the -3, seconds to the -1. That would be the value of the rate constant. In other words, now that we know K and the value of N and the value of M and the value of L, we know exactly what the rate's going to be at any moment. Okay, so we could substitute those values back in. So that's how you can solve for the rate constant and take into account what the units are. The units really depend on each reaction. They depend on how the rate law is set up and the orders of the reactants. There's always going to be a per second in the rate constant, but this part with molarity, that's just enough molarities to divide out 3 of these, leaving 1 behind, so you get molarity per second as your units for rate. Anyway, but that's how you can solve for the rate constant as well. The rate law, if people talk about the rate law, they're looking for something like this, where you've just specified the orders of each reactant. And if an order happens to be 0, you could potentially just leave it out because you'd just be multiplying by 1. Okay, so let's go ahead and leave it there.